Welcome. Thank you for coming, and thank you that you decided to make a presentation for us. This is Introduction to Radiation Hardness Assurance for Space Missions. Very important for us because our objects are in space and they are also exposed to radiation, and we have with this program. And also these biological structures that we are dealing with are also exposed to the radiation, and this is very important problem. Please, floor is yours.
Okay, thank you, Professor. So good afternoon, everyone. My name is Tomasz Rajkowski. I'm a postdoctoral researcher at the National Center for Nuclear Research in Otwock. I'm also a radiation hardness assurance engineer and consultant for some space companies. I have experience in aerospace engineering. I was for 7 years in the Space Research Center as a test engineer, as a hardware engineer, and then project manager. Then I did my PhD in radiation effects to electronics in University of Montpellier in France. Also doing research for the 3D Plus company, working on the radiation hardness assurance programs for the whole systems. And yeah, I have great pleasure to be here to present to you this topic. And yeah, let's start. So before I present the agenda, just a few slides telling why the radiation in space is important. So I will start with the story of what happened in 2003, in end of October and beginning of November. So that's why it was called the Halloween storm. It was the super huge activity of the sun observed at that point, at that moment, and it affected not only the power grids on Earth, but also the electronics and other parts of the spacecraft. So we could observe some of the spacecraft loss, like ADOS-2, some instruments damaged, like EPAM on ACE or instrument Marie of the Mars Odyssey, some solar panels damaged, some other subsystems damaged temporarily or for a longer period. There are problems with error rates and in general with the functionality of many spacecraft and subsystems. And this example is pretty important because it can tell us that yes, radiation, in this particular case, radiation from sun, can affect the electronics of our spacecraft. Because sometimes when a big satellite or important satellite has some problems in orbit, especially at early phases, the management likes to say, oh, it's probably due to radiation, because that's something that we cannot measure, in fact. Yeah, it's very difficult to say that, okay, this satellite had problem with radiation. It's pretty difficult to track this. But this case tells us that, okay, there's strong correlation. We observed huge activity of the sun, and then a lot of spacecraft had problems. So I like to show this picture to the audience to have this impression of what might happen. But to be clear, that was the very special case, very intense activity of the sun, not something usual, something that happens once per many years. But yeah, so radiation can do severe damage, severe harm to our electronics, to our spacecraft. Another reason why the topic is important now is because we are in the new space age. I guess you know this guy. I've heard that there's a lot of hype about space now in Krakow. So really big congrats for this this project. So yeah, if we talk about new space, this means that there's huge increase in number of satellites launched and number of electronics in space. And because the price of the launches and developing the spacecraft is getting lower, we also need the lower price of the electronics. So we move to using so-called the COTS components, commercial off-the-shelf components. So the components that were not especially designed and tested to be used in space, but the processors, memories that you have in your smartphones, laptops, and so on. And people select these components and try to adapt to the use in space. And this means that now a lot of effort related to assuring that these components will survive the radiation is shifted from the manufacturer of the component to the satellite developer. Because if we have money to use the radiation hardened, radiation tolerant component, which costs really a lot, then the manufacturer takes care of the radiation qualification. But now, if we take the much cheaper, but usually pretty useful components, the COTS components, now we are responsible for the radiation hardness assurance and the radiation qualification of these electronics. So that's also why it's important to understand the topic pretty well. But I have also some disclaimer. There are also some other problems with electronics and on radiation. So first, if you want to launch something, make sure that you have the correct design. You made the worst case analysis, the thermal, mechanical, vacuum testing. You have the positive power balance. You took care of the configuration control. There are many things to think about. And then once it's pretty well working and you know it shall work and it's launched, then the radiation starts. Yeah. So I know something about radiation, so I'll talk about the radiation, but just to be clear, it's not the only threat for your electronics. So the agenda for this afternoon is that I will start with the radiation environment description, focusing on Earth's surrounding. Then I will tell in a few words about the radiation effects in electronics. How do we test the electronics to know the radiation response? And then I will describe briefly the typical approach for the radiation hardness assurance. So the environment around Earth, the radiation environment, is made by the particles from three main sources, or two sources and some of the modulator, as they call it. So we have a lot of protons, electrons, and a bit less of heavier ions from the sun. We have we have rare but very energetic particles from the deep space. And then some of them are trapped in the magnetic field of the Earth, constituting the Van Allen belts, so the radiation belts. And when we talk about the radiation effects to electronics, we are mainly interested in these high energy particles. So about solar radiation, these are particles and electromagnetic radiation. The third thing is that we have the solar wind. So it's this constant flow of low energy particles. But we have also the solar storms. So they are events with particles of higher energies. They're relatively short but intense events. We have here solar flares or coronal mass ejection. And it's good to know that the solar activity is changing in cycles, 11-year cycles. And these cycles were measured since the 17th century first by measuring numbers of sunspots. If there were more sunspots, there was higher sun activity, less sunspots, lower activity. So we know that these cycles are pretty irregular. So by the way, now we are around the solar maximum. So good luck, hype. But yeah, that's true. What does it mean to around solar maximum of the solar activity, that it is higher probability that there will be more of this solar storm events. Now, regarding the deep space, we have so-called galactic cosmic rays. So, as I said, we have here low fluences of particles, so low number of particles, but they have really high energies. And what's interesting, the intensity is inversely proportional to the sun activity. So somehow, I like to show it on this picture in the top right. This high peaks means that we have this solar storms, so the activity of the sun, some events related to the sun. So we have the maximum solar activity where there are many of these peaks. Yeah. But when we have no these peaks, like here and here, we have minimum of the solar activity, but then the GCR background level is higher. So somehow interesting that the lower sun activity, the more the GCR we have. Yeah, and there are not so many of these particles. So, as I said, fluences are low, but they have really high energy. And if they hit the sensitive node, we may have problems with the destructive effects in our electronics. And then we have the radiation belts. We have here the proton belt, the lower one, and the electron belt. As I said, they are mainly made of the particles that came from the sun, but also from a bit from the GCRs, but mainly from the sun, that were trapped in the magnetic field of the Earth. And we have here also so-called South Atlantic anomaly, because the magnetic field is not homogeneous. It's not the same in all the parts around the Earth. It's a bit weaker above the South Atlantic. So here we observe a much higher levels of the particles, namely protons, in this area. It was measured by the satellite POES for more than 13 years. So we can see that the typical flux is like 4 to 5 orders of magnitude higher than in all other regions. And it's a bit old graphics, but I like it because it can summarize particles from different sources and of different energies that we meet in Earth's orbits. So starting from the low energies, we have the solar wind, protons, and there's some electrons. And we have the higher number of particles are these of the lowest energies. Then when we move to the higher energies, we have this trapped protons and trapped electrons, so the radiation belts, and also the solar storm protons. When going to even higher energies, we have the solar flare protons, trapped protons in the inner zone, so the lower belt, and the highest energies are of the galactic cosmic rays. So as I said, we have the lowest flux of GCR, but they are of really the highest energy. And I'll be talking in a few minutes about the radiation effects, but even now I may announce that somewhere here around 1 MeV is the level when the single event effects starts. So below all those particles with high fluences, high fluxes, will be the source of the cumulative effects. So we need many of the particles to come to do some damage to our electronics. But starting from here, it's enough that one energetic particles strikes the sensitive part of our electronics to trigger some effect. we have some tools to model the radiation that we are going to meet in space, in orbit. For example, we have the OMR. Here you can input the exact data of your orbit, and then it can tell you, for example, this higher upper left plot, depending on the aluminum shielding, what TID level, what the dose level you're going to have in your spacecraft. Also, for the specific orbit, it will give you the what is called LET spectrum. So LET is the linear energy transfer. I will tell about this in like 15 minutes. But this plot is important to calculate the single event effects error rate in your spacecraft. Also, if you take more advanced tool like FastRad, you can input your CAD model to this tool. You can input the environmental model, for example, from the OMR, and then it will show you what's the expected level of the TID, the dose, the radiation, in each point of your design. So, you know, if there are some sensitive nodes, they probably should be put somewhere here with this blue region, and not here when it's red region, yeah. And by the way, it looks like here it's very close with this red region. It's very close to the spacecraft side panels because it's somehow exposed to the radiation from the external to the spacecraft. Probably that's why it's here red. We have also another tool. It's made pretty recently by the Space Radiation Services. Here you can, for example, select the duration of your mission. You can take, for example, some shielding that you have, and then depending on the altitude and the inclination of the orbit, you can have the information of the expected radiation level. So here it's not so big, the radiation, but then going higher, we are closer or even inside of the lower radiation belt, so the proton belt. That's why we have this high intensity and high dose of the radiation. Yeah, so I think that at this point we'll be done with the first part about the radiation environment. So I think what I would like you to remember is that, yeah, for sure the radiation depends on the orbit you choose. That's nicely depicted here. And it will depend on the time you spend in orbit, especially for the cumulative effects, because for the single effects, they are a threat from the very first moment once you're in space. But the radiation will also depend on the sun activity. So when you launch your satellite, your spacecraft, during the higher activity of the sun, there will be more radiation than during lower activity of the sun. If you have any questions, feel free to ask.
So I have a question about this earlier slide from the presentation. Did I understand correctly? No, this one, but the beginning. Don't worry about it. Did I understand correctly that during solar storms there is a smaller chance for a cosmic ray to hit Earth or something around Earth? Did I understand that correctly?
Yes, during higher solar activity related to this 11-year cycles. So in the maximum of the solar activity, the number of GCRs, so the galactic cosmic rays, is usually lower.
Is that because the solar activities push them away or something like that? How does that work?
I don't know exactly how does it work, but I know the measurement that it's like this.
Okay.
I don't know the mechanism behind, but
okay.
Yeah.
What kind of shields are we using to shield ourselves from different kind of radiation in space? Is it like metal composites or something totally different?
So usually to shield against protons, we use the lighter metals like aluminum, or in general lighter materials. to not have too many secondary particles that will be a threat for our electronics. And then to shield against electrons, it's nice to have, it seems that the heavier materials are more effective.
So you're trying to combine both so you can get the best shield effect, or is it like you're using different depending on what you're trying to shoot from?
Rather we use the material that is, let's say, accurate for the environment that we are going to meet. So if we know that we'll be flying a lot in the higher radiation belt and the electrons, then we'll need to find the material that will stop electrons more efficiently. But usually we fly in the environment where we meet more protons, either from the lower radiation belt or from the sun. So then the lighter materials are better.
I have one more question. If we have a mission to the moon, so we just fly through the Van Allen belts, should we care about the radiation during the flight in Van Allen belts, or is so small period that the idea will be like small enough to just ignore it?
For those online who didn't hear the question, it's about the way to the moon, and yeah. So it depends if you are already active or if you will be activated once in the moon orbit, because and it depends on the period you spend in the radiation belts. If it's like hours or days, I would not worry about too much. But still, if it happens that you are orbiting a few days in this area, like 2,000 kilometers above Earth, yeah, and few days, but you really can accommodate much more radiation than for a few years in like 500 kilometers, yeah. So you should first thing know how long time you will spend where, yeah. And usually when our electronics is switched off, it's less sensitive to radiation. Usually, not always. For some components, it is the worst case when they are switched off. So yeah, it depends on if you are switched on or off, and on the period you spend in the proximity of the radiation belts. But the good thing is that if you are switched off, you do not worry about single event effects.
I have also a question. I understood that this environment, space environment, is very dynamic if we consider the radiation. How dynamic it is? How quick change can occur in the radiation?
Okay, so the question is about the dynamics of the radiation environment. So
it is days, it is months, or it is hours or seconds.
Yeah, it's more like hours and days in terms of the solar storms. Yeah, so they are unpredictable or very difficult to predict. Usually you do not know that it already started and it already may affect your electronics, because once we start to measure it, it already probably hits your electronics. So those are the most dynamic ones, yeah.
It means that it is very difficult to predict, yeah. It will occur or not occur during the launch, yeah.
Yeah.
Okay, that is a question to the previous slide. Yeah, you make the prediction of the influence of the radiation to the electronics, yeah, and the geometry. What is the input data? If it is very uncertainty because we don't know.
Yeah, so here are two things. This solar storms are a threat with single event effects. So from one day to another, you may have several orders of magnitude higher probability of single event effects. And those simulations like here on this right side are the TID effects, so of the total dose. And even if due to solar storm we have like 1 K-rad or 500 rad more radiation, it's something comparable to what we have in, I know, 1 month or a few months of normal operation. So this is something that is done by the cumulative effects. So the impact of particles that are still coming from the sun and from the deep space and from the proton belts of usually lower energies, and they still accumulate the dose. Here's the higher dose, here's the lower dose. And if there's some storm, so in like one day you may have a bit higher dose everywhere, but still the proportions will be the same.
Okay, means that you should take into account the exposition time, yeah?
Yeah.
For calculation.
Yeah.
Okay.
Okay, I think I'll move forward.
We also have one question from online audience. Maybe I can just read it out loud. Is there a cumulative effect of radiation on electronics, for example, caused by multiple passes through Van Allen belts? This is the first question. And also, which type of radiation is most harmful to the electronics? What are the best practical materials for electronics protection against radiation?
Okay, so
this is
about the
electric.
Yeah, I think thanks for the question from the chat, and I think I will try to answer all those things later during the lecture.
Okay.
And about
my proposal is we stop discussion now. We will start the discussion after the presentation because we never finish.
Okay, so the next stop for the questions will be in the end. Yeah, I hope that some of the questions we have now will be answered, and I'll try to answer more later on. So what are the effects of radiation in materials? So as I said, we have 3 main sources of radiation, namely the radiation belts, the sun, and the galactic cosmic rays, but there are also various types of particles. And this various types of particles may impact electronics in different ways. So one thing is that we may have something called displacement damage. So the semiconductor crystal structure damaged. So it's a kind of cumulative effect. So we need a lot of particles to come, particles with high enough mass to damage enough the structure of the semiconductor to observe this displacement damage effect. And that's why mainly protons contribute to the displacement damage, because they are heavy enough, heavier than electrons, and they are high enough in number. So you have high fluences of protons. That's why they will contribute to this displacement damage effect. Electrons, we have plenty of electrons as well, but they are not so heavy. And heavier ions are so rare that they will very slowly contribute to the displacement damage. Another thing, we have 2 effects due to ionization, direct or indirect. So one thing, if the ionization happens in the oxide, and we have the trapped charges here, made by the, again, cumulated impact of many particles, we have something called total ionizing dose. And here we need also a lot of particles, and we need the ionization from those particles. So both protons and electrons will be the source of the total ionizing dose effect. And the last effect, but not least, surely, are the single event effects. So the ionization that happens here in the semiconductor area, So the ion or proton passing, generating the positive and negative charge. And for this, the source is mainly from heavy ions because they have energy high enough to ionize locally very strongly the material, but also from protons. From protons, it's sometimes direct and usually it's indirect ionization. Indirect, I mean that the proton is hitting some ion in the crystal of the semiconductor and is pushing away from this position, and the secondary particle is ionizing. That's the indirect ionization. So we know how these various particles may produce these radiation effects. And then, yeah, I said that these are cumulative effects, displacement damage and TID, because we just need a lot of particles to start this effect to be important. And for SCE, it is induced by a single particle. And what technologies of electronics are sensitive? So for TID, I think whatever you think, it will be, whatever component you may imagine, it will be usually sensitive to TID. So various types of transistors and integrated circuits, some optoelectronics, MEMS devices, oscillators, and many more. The full list is in this ECSS document from ESA. And for the single event effects, the most sensitive are the digital chips like memories, FPGAs, microprocessors, for example, SU effects or latch-ups, but also in analog chips and our MOS transistor there are different types of single event effects that happens, but they also happen in optoelectronics. And for the displacement damage, the number of technologies that are sensitive is smaller. We have here the bipolar components, electro-optic sensors, optocouplers, or photovoltaics. And from this point on, I will focus on the TID and SE effects as they are more important. So here I will just present a few examples of what TID effects, so cumulative effect, may let's say trigger in your electronics, may do in your electronics. So this plot, you can see result of the radiation testing, TID testing of transistors. So this solid black one is the pre-rad, so the IDS to VGS plot for the component before radiation. So we can see that the gate source voltage of 0 volts, there's no current flowing, yeah, or very, very low. So it's switched off, so it's how it should look like, yeah. But then when we irradiate the component, we see that it starts to open and conduct current, even if there's 0 volts of the VDS voltage. So we call it that the threshold voltage of the transistor is shifting. And it's the key, let's say, effect in the MOS transistors. And as you know, a lot of digital electronics is made of MOS transistors. So this impacts other effects in the integrated circuits that we have. So for example, if we observe some current increase, here's the EFRA memory that was irradiated to several hundred K-rad, and normally it was consuming very low current of, I know, some microamps, but then at some point it started to consume more and more current, and it's somehow related to also this threshold voltage shift of transistors that are inside there. But also due to TID, at some point we start to observe functional failures. Yeah, so here from about 200 K-rad, some problems with reading or writing to the memory or refreshing memory started. Also, this transistor switching voltage shift, another effect related is the propagation delays here in the FPGA. So before the irradiation had no delays, but then after 25 karat we have like 10% longer delays. So if we have some signal path inside of the FPGA and we know that it's working with the clock cycles correctly before the irradiation, we cannot be sure if it will meet the time requirements after the irradiation, because the propagation is getting longer. And the interesting thing is here that there's no step answer, but from the very low irradiation levels, the degradation starts. For the bipolar transistors, we have, for example, the current gain degradation. So here we have for various collector currents shown that before irradiation is the solid, the full symbols, and after radiation these are those empty symbols. So also depending on the current, the collector current, this effect is stronger or less strong, but it happens. So now the key single event effects, and I want to show. So normally we talk about destructive and non-destructive effects. So we have the single event latch up for the destructive ones and single event burnout or gate rupture. Latch up is very important because all the CMOS chips are potentially sensitive to latch up. CMOS is the technology very popular in designing digital components now, so the processors, memories, and so on, FPGAs. So it's important to know if the component is sensitive to latch up and what's the level of sensitivity. This SEB or SEGR are more typical to PowerMOS transistors. They're also destructive, yeah, but let's say limited to very specific group of components. With the non-destructive, we have the single event upset, transient, and functional interrupt. I'll tell in a few words more about them. But these are the key ones. If you want to read more, here's the list from ECSS of other effects. But from my point of view, they are less important. Or okay, at first stage, you need to take care about these effects, then you may think about others. Or some of them are also limited to some special technologies. So about the single event latch up. So when we develop a CMOS device, we have some doping areas that may produce something called parasitic thyristor. So thyristor is shown here is combination of the PNP and NPN transistors connected like this, and even though the manufacturer doesn't want it, it just happens that such structures are inside of the CMOS devices, and normally they are switched off. But sometimes it happens that a single charge particle may deposit a charge in the way that the thyristor starts to operate. So, for example, we have this charge deposited here on the RP well. So the NPN transistor starts to open and the current starts to flow. So the voltage here decreases and the PNP transistor also starts to open. And we have this effect of domino that because here the voltage increases, here goes more current, so here decreases voltage, so here goes even more current, and at some point we have a path of the current flowing from the positive voltage to the ground. So if we do not start this quickly, it will overheat our device and destroy it. So that's why it's the destructive effect. But the good thing is that if we act quickly enough, we can stop it. So switch off the device, wait for some milliseconds or seconds, maybe rather seconds. And then when we switch on the device, there should be no more of the latch up here, and the device should operate normally. But if it's too late, then it's overheated, and it can like not work in two ways. So not work and consume no current, or not work and consume a lot of current. But we have also some softer effects. So for example, transient. It's a temporal change of the voltage or current in the node of the electronic device. We have some examples here. So when the particle comes, we have this voltage change, some glitch or something like this. And if it happens in, for example, analog devices, like power devices, you may filter it out. So if you have some filter after the device, it should be mitigated, but sometimes it may force another device to switch off, or even in extreme cases to destroy it if the voltage exceeds the acceptable voltage of the device that is connected to the on this line. We have also single and upsets. So it happens when the charge is changing the state, logical state, at some point of the memory or of the buffer of the flip-flop or the configuration memory of the FPGA. So in every device where we have the logical state somehow remembered, we have some kind of memory. Usually it may be changed from 0 to 1 or from 1 to 0 by a single event upset. And depending on the criticality of this memory part, it may lead, it may be even not seen, it may corrupt your data, or it may lead to some failures in the program execution. Or it may lead to CFI, I will tell you in a minute, or even whole subsystem temporal failure. And the CFI is the interruption that makes your chip stop working correctly. So it may reset or hang or enter another mode of operation. But normally when you reset or do another maneuver, you can restore the normal operation. Okay, so here I'll not ask for questions will be later, but just what I would like you to remember about the radiation effects, I think is this, let's say, comparison or division to cumulative and single event effects. So cumulative, where you need a lot of particles to come and to affect your electronics, to observe the effect, to observe that something is degrading. And single event effect, where you need only one particle passing through a sensitive node of your device to observe the effect, potentially destructive. And now, to know how sensitive our devices are to the radiation and to those effects, we do the testing, so radiation testing. I'll start with TID testing. It's a bit easier. Here is the container with the cobalt-60 source and many boards that are irradiated with this radiation source for the TID testing. So even from this photo, you can see that one thing is that you can have many boards irradiated at the same time. Yeah, and another thing is that depending on the proximity to the source, you have higher dose rate, so higher intensity of the beam if you are very close, or lower dose rate if you are further from the beam. So usually for TID testing, we start with the initial measurements, then we do the first radiation, measure our device after a specific dose, and then repeat the irradiation, measure again, repeat, measure again, to the point that we needed the device to survive or upon failure of the device. Then for CMOS technology, we need the annealing, first in room temperature and then in 100 degrees. And then we have the final measurements and data analysis. And the procedure and all the specifications in this ESCC 22900 document. The standard source is cobalt-60, although sometimes we use some alternatives. And typically, we irradiate 5 components biased, so the nominal supply voltage, or rather worst case supply voltage, 5 components unbiased, and we have 1 sample, a control sample. Yeah, we have, as I just said, irradiations in steps, for example, every 5 kRad. 5 kRad is not a lot, but not so low. I know, I think that's the amount that your HYPE satellite will meet in, 2 years. That's, for example, something like this. Yeah, here also the dose rate is important for bipolar components. Dose rate, so the intensity of the beam, because it was shown that for some of the bipolar components, the effect, the degradation might be different if we deposit the dose in, for example, few hours or few weeks. If we deposit the dose in a few weeks, the degradation will be much stronger for some of the bipolar components. That's one of the complicated things with the TID testing. On the other hand, for the CMOS, we need this annealing, so putting in room and then in high temperature these components. Yeah, and usually we consider the TID test as destructive ones. Here's the graphics showing how the very nice irradiation facility at ESA looks like. So we have this very strong 2000 curie cobalt-60 source, some remote positioning system, trolley, and we have some feed tubes, so we can, from the control room, connect to our device during the radiation. So even we don't need to stop for the measurements, but we just can measure everything during the irradiation. Now with single event effects testing. So here we use the heavy ion or proton testing. With the heavy ion testing, you can see here the vacuum chamber, because if we do not have the high enough energy of ions, we need to put our devices in the vacuum chamber so that the ions do not stop in air, but they stop in our device and deposit the charge there. For the protons, if the energy is above around 30 MeV, we do not need to do the irradiation in a vacuum chamber. Yeah, I'll also say about a few differences between heavy ions and protons later. But the key points are, okay, so we have this ESCC 2500 specification. We use heavy ions or protons. Here we use small sample size, usually 3 samples, but also in the worst case conditions. So for example, for the latch-up, the worst case condition is the highest temperature the component may survive. So for the space grade components, we usually see the reports that it was tested with heavy ions against latch-up at 125 degrees Celsius. The complication here is that the monitoring for the single event effects is during the irradiation. So it's a huge complication of the test setup, because I just said that with TID testing, we can irradiate, take the board on our table, measure everything, and after 1 to 2 hours, put it back to the beam. But with single effects, all the interesting things happen when the beam is on, and we need to monitor everything. And if we take into account that the irradiation is when the electron is in the vacuum chamber, then we need to fit through to go to the vacuum chamber with our cables. And then usually, if we want to be safe with our electronics or ourselves from the radiation, we need to go further so that the cables become long. So the complexity is pretty big here. Yeah, and typical fluences for the test are 10 to 7 ions per square centimeter or 10 to 11 protons. This is the order of magnitude interesting for us. Yeah, and the limited heavy ions penetration is just set describing the picture that you usually need to perform the testing in vacuum, but also to not stop the ions in the package of our chip. Usually we open the package so that the chip is, so the silicon die is exposed to the radiation, because the penetration is might be limited to like tens or hundreds of microns. So we don't want it to stop in the plastic, but we want it to stop in a silicon die and to observe the effects that are interesting for us. So how do we measure those SEEs? Here's an example of heavy ion test, single upsets in FPGAs. So we take the ions with various LET, so linear energy transfer, that depends on the energy and mass of the ion. And usually the higher the LET, the stronger the effect. So the higher probability that we will observe the effect. That's why usually the cross-section, that's how we call it, looks like this. It's a higher level here, and with going to lower LETs, it's decreasing. And so the cross-section, SC cross-section, describes the component's sensitivity and how we measure it. So for each LET value of the ion, so in fact each species of the ion, because here in this cocktail we took 4 different ions to obtain this plot, we irradiate with certain fluence, like 10 to 7 of ions, and then here we count how many SUVs we have, how many upsets. We write down, okay, we decrease the LET, again irradiate, how many here, okay, we write down, and then we just divide number of effects by the fluence, and we have the cross-section like here. What's interesting here is that we have always the cross-section saturation region, so we know that even increasing the LET will not obtain more upsets because it's saturated here. And we have also the LET threshold. So the LET value when the effect starts. And those 2 values, so threshold and saturation region, are pretty important to calculate later the error rates in orbit. Because as we have the LET spectrum in our orbit that I showed you like 15 minutes ago, so we know how many particles with specific LET value we have in orbit. And then we have the sensitivity of our components. We may calculate what will be the error rate. So how many errors to expect normally in orbit. If we test with protons, we obtain similar cross sections, but here we have the proton energy, not the LET. And some comparison of heavy ions and protons. So the heavy ions induce the most destructive SCs, and protons usually the soft errors, and very rarely the destructive ones. And here there's direct generation of simulant effects, and here's indirect or direct. So if we want to check if our device is sensitive to latch-up, as I said, latch-up is this destructive effect, very popular in that might happen in each CMOS device. we need heavy ions. Usually protons will not tell us if latch-up is there. So heavy ions has lower penetration than protons, and the availability of facilities also lower. But what is higher is the price here. Usually starts from thousands of euros, but some very specific high energy heavy ion facilities in US may cost like $4,000 per hour. And for protons, we have usually a bit less than for heavy ions, the price per hour, but recently not so much less. Okay, now some think about facilities that we have in Poland. So you're lucky here in Kraków because you have one of the best radiation facilities in Poland, or the best one. So in the Institute of Nuclear Physics, you have the 60 MeV protons with the radiation field diameter up to 12 centimeters, so we can like irradiate even a whole board of your electronics there. And 60 MeV means that usually it's high energy enough to not test in vacuum, but in air, and it can penetrate packages and deposit charge in your electronics, so it's cool. And the beamline in this institute is shown here. You have also 200 MeV in this institute, but usually they are used for oncological treatment, and as far as I know, it's very difficult to get the electronics testing. You have also here the cobalt-60 source with the radiation area 20 by 20 square centimeter, and those range from 3 to 12 kRad per hour. So not really suitable for bipolar component testing, but for normal digital electronics, it's very good. In my institute close to Warsaw, we have also high energy X-rays for TID testing that already was used in several new space projects in the last years. And we also have big ambitions to have protons. This should happen pretty soon, and also in the further future, the cobalt-60 source. And about radiation facilities in Europe, here I focus on single event effects testing because TID facilities are more popular. So we have the very good RADEV and UCL heavy ion facilities. Here is given the availability barrier, so like 12 weeks per year or 16 weeks per year for the electronics testing for space. We have also heavy ions in GANU or GSI, CERN. We have also some proton facilities in Groningen or in ESA in Switzerland. Also pretty new proton trap center in Holland with 200 MeV protons, or in south of France 60 MeV protons. There are more details here given with the range or price per hour, but I will not read all this stuff. Yeah, so this will be the end of section 3. So the testing. Here I think that the most important thing I wanted to show is the complexity of single event effects testing. So we don't have too much facilities. In general, heavy ion facilities that are needed for destructive effects testing. For the TID, we have more facilities and it's easier. So it's good, but for the single event effects, it's not so easy. And finally, the typical approach for the radiation hardness assurance. So I wanted to show this graph and how we usually approach the so how we usually approach the problem. So we start with defining the environment. We know our orbit and we have the radiation models, so we can define the radiation environment. Also, knowing more or less our structure of the satellite, we know what the environment will be inside. Yeah, we can have it with the OMER software or with FastStart software. if we have the more detailed mechanical design. Then comes the requirements definition. So here, when we have the mission requirements, so we know what is the expected performance or the functionality of our mission, we need to map those requirements to the requirements of the electronic components. And they need to be smart, yeah, to not kill the mission, so to have high enough expectations from our electronics so that no destructive effects happens, or if the destructive effects are mitigated, or that our spacecraft will not die too quickly due to TID. But they also need to not kill the budget, yeah, because if we give too strong requirements, we need to go for the components that are really costly, and it will not be manageable. So when we have the requirements, then we evaluate the design components. So we take a look of what we want to use in our design or what is possible to use. We take the data from the manufacturer or the test data that we have or from the radiation databases, and yeah, we validate if it's gonna work or not. And then if it's gonna work more or less, then we need to work on this so it's gonna work more. Yeah, so we need to, it's the moment to apply some mitigation techniques, mitigation schemes. So mitigation techniques, so some techniques to make the consequences of some effects we observe not so severe for our spacecraft. So to detect some effects and to act quickly for so that do not harm to our spacecraft. Yeah, but sometimes it happens that it doesn't fit everything, so we iterate the process. So if the mitigation techniques doesn't work, then we need to maybe change the components, or maybe we need to put more shielding to the spacecraft so that the TID requirement is lower for the design. Yeah, so it's the iterative process. So it might be very expensive, the radiation hardness assurance, so where to look for savings? I would tell that by allowing more risk while understanding what the risk is. So first thing, we focus on the critical components, not everything, but if we can, then we focus on the critical components. Yeah, we may reduce the test effort, so also the cost of testing, by accepting higher soft error rate. So proton testing instead of heavy ion testing, board level testing, or by testing lower sample size. So if we test, you know, 2 or 1 chip instead of 3, then there is some risk that it's not very representative as 3 chips that we test, but it reduces the cost. But what should be remembered here, that for the destructive singular effects, heavy ions are needed. Yeah. So we may allow some risk, but not all the risk if you want to survive. And in some cases, using COTS components instead of rad hard ones may save money. I wrote this for purpose, that it's in some cases, because it's not always like this, because it may happen that you think, okay, I will take the cheaper COTS component, but then you go for testing and the testing is in phase, let's say B2, C of your project, and you see that this component is rubbish, you need to change for another one, and you're in the middle of your project. So you took a very cheap component, it was really cheap, but then you're in the middle of your project and you need to change a lot of things, so it happened to be not so cheap. Yeah, but in particular, when the COTS components was already tested with heavy ions and fits well the design, it's probably the might be the good choice. But it also depends on the mission class that you want to have. And the level of acceptable risk depends on this mission. Please do not read everything. This table is from the very nice presentation from the V.S. Gupta from ESA, and it's how ESA approaches radiation hardness assurance and risk acceptance for various mission classes. So for mission 1 and 2, so the biggest ones, when the failure is not an option, then you need to follow strictly the ECSS. When you need to test with heavy ions, you test with heavy ions, and no risk accepted. But then for the class 3, more risk is accepted, and then it goes class 4, class 5, the demonstrations and educational missions. Then the requirements are really, really relaxed when compared to class 1, and the cost of the radiation hardness assurance is lower here. So for example, no TID assessment required. Yeah. So you just don't care for TID because you know that the mission is short. Single effects heavy ion testing on if power MOSFET and overcurrent protection parts, and you can do it at board level. Also proton testing at board level, and heavy ion testing only up to LET of 38. Here normally it's 60. It also makes a difference because much more components will survive 38 MeV square centimeter per milligram than 60. Okay, I think that's the end of the whole presentation. And from the part 4, I wanted you to remember how we approach the radiation hardness assurance, and also that the risk we may accept depends on the mission that we have. Okay, thank you.
Thank you very much for your presentation. I think that now we can open the questions that we all have. So, welcome.
So I have a question regarding the influence of the temperature on the TID. Is there a correlation between the how much of the kilorats component can take in different temperatures?
Yeah, so for the online guest, the question is about the TID and the temperature. So in general, when we test against TID and we want to test in the worst case conditions, we mean the bias conditions, not the temperature conditions. So it should not change too much. And usually we test in room temperature conditions. But then it may happen that when we heat up the device after the irradiation, the performance is restored. So the degradation is getting lower. Yeah.
Okay. I have a question about SE testing. If we have a mission that doesn't last long and it exposed only for protons or heavy ions, the most maybe sensitive part would be a memory on the board. But what about the processor? Should we also test processor against SE and protect it somehow, or what are the standards?
Okay, so the question is about the short mission where we have protons, heavy ions, probably around moon. Yes. Yeah, and we have the memory that we want to test, but also we have the processor on board. And the question is about the criticality. So I would say that for sure both of them are critical. Yeah, so it depends on the function of the component in the subsystem or the system. But I can imagine that if you want to control something or store data and send data, then you need the processor. So probably both of them are equally critical.
In many cases, you have considered here, you just measure some effects of irradiation. For instance, current consumption, for instance, current gain change, and so on. Also, structure damage. But in all these cases, we have to consider it. We have to consider this effects of crystallographic of the material. It means some defects, dislocations, grains, and so on. Could you little bit more explain about this, what you said, structured image? What is it in your view?
Okay, so now the question about the structured image is not the strong point of my knowledge, I would say. But usually it may happen in the bipolar technologies or in some optoelectronics, that is that you want to measure or capture the image, yeah. Yeah, I'm not sure if you want to know more about the effects there or what we observe, or I'm not sure.
Yeah, a little bit more about, for instance, structured image, what it means. Density of vacancy increases or something else?
Yeah. Okay, so yeah, density of vacancies for sure. Yeah, that's the main, let's say, mechanism behind, and then it may be manifested by I know, for example, random telegraph signal in some photodetectors, or some functional failures in some CCD matrices, and effects like this. But as I said, I'm in this effect, I'm not very expert.
However, I think you can agree that this consideration is very important, because structured image, it is just measuring something by some device, but we have to understand mechanism of this.
Yeah, for sure. Yeah, and to develop the devices that are, let's say, hardened for this effect, we need to understand the mechanism. That's for sure. Okay, so I read the question that so in biology, the primary concern is not only high energy protons such as GCRs, but also secondary radiation like X-rays, which are generated when high energy particles pass through spacecraft shielding. Is there a method to predict the level of secondary radiation that might be encountered along a specific flight path or to or through orbit? So yes, the first thing for this prediction, we need to have the information on the radiation and this specific orbit or flight path. And then if we have this radiation, then we can use, for example, Monte Carlo tools like GEANT4, FLUCA, and other tools like this, which will simulate what happens with the radiation while passing through the shielding or other materials. And then we may have the information about the secondary particles. Okay, there's a question about slide 17. Okay, so is the trend linear with those? I think for many, okay, there are some transistors with the linear trend, yes. They are even sometimes used for as dosimeters to measure the exposed dose. Yeah, so I think yes, but I'm not sure if for all the transistors. Okay, for years there was a trend to reduce transistor size in the electronics, reaching now single digit of nanometers. What is the limit for electronic chips used for space applications, hardened and non-hardened? So it's a question about the prediction, yes. So it looks like that with TID, the reducing the feature size increases the hardness of the chips, but for single effects it's opposite, and single particles may deposit may cause bit flips in many memory cells. What is the limit for electronics chips used for space applications, hardened and non-hardened? I'm not sure how to answer on this question, because with the codes, it depends on the mission you want to have, and it depends on your expectations and the level of reliability you want to have with specific mission. Yeah, so for one application, the specific component may be suitable, and for another one not suitable. And for the hardened chips, the technology they use, I'm not aware of what technology is usually used, in fact, and very often they don't want to share it, so I'm not an expert here. For COTS components, is the number of samples defined in ESCC sufficient? I guess it's the question about TID or single effects testing. Again, these numbers that you need, for example, 10 components tested or 3 for single effects testing, it comes from the part-to-part variability. So you may have components from the same lot, and they have some variability. That's why you need to test more devices, in particular for TID testing. And now, if we are testing COTS components, if we have nice traceability, so we know that these components come from the same manufacturing lab, and they are really from the same lot, they should behave very similarly. So I guess the number of samples should be okay. But if you are not sure, then you have a problem. On slide 13. What CPU and GPU were tested in brand supplier type? Okay, so all this information is in the source given below. This radiation effects data workshop is the very good source of the radiation data. It's the data workshop related to the NSRC conference, which happens each year in the US, or last year was Canada, but normally in the US. And they have always this data workshop, and they have a lot of resources about radiation data there. So we aim to go deeper to this source to know what device was tested. And there's a question, would the presentation be available somehow? For me, it's okay. So yes. And examples of mitigation schemes. Okay. Slide 38. Yeah. Okay, so the mitigation scheme is, for example, the overcurrent protection. So to act to the latch up the unit may have. So to quickly shut down the device so that it doesn't overheat and is not destroyed by the latch up effect. For example, the TMR, so triple modular redundancy. If you have very important memory content that you want to survive, you put it in 3 different memories, so that even they are affected by upsets somehow. You may do voting between 3 different memories and restore the right data. For the functional interrupts, you have, for example, watchdogs. So if your component starts to fail or is entering some not normal mode, or even your subsystem, then you may have the watchdog, which will reset pretty quickly your subsystem or the whole satellite. So you don't need to wait to pass over the ground station to connect and see, okay, we have a problem, so we reset and so on, but you can restart more quickly, so you can save some availability of the system. Yeah, I also encourage to contact me for more resources on this. Yeah, normal devices took to space. They tried to use them. I think that the first thing is that ISS is not so harsh environment. Okay, unless you are passing the South Atlantic anomaly, it's not so terrible there. So I guess it should work somehow. But I have no idea if they are regular laptops or some hardened ones. Okay, not sure if this one was answered. What are the best practical materials for electronics protection against radiation? So yeah, I tried to answer this before, but to take it quickly is for proton irradiation, you rather take lighter materials so that the secondary particles do not harm your electronics more than those protons. And for the electrons, you usually take heavier materials. But also you can contact me and I can maybe find more precise information. Okay, which components are more affected by TID or SC in unbiased conditions? Is this a case for flash memory? What is the exact reason and how to approach trade-offs like this? For SCE, SCE does not happen when the device is unbiased. It only happens when the device is biased. So when we are switched off, we are safe from SCE. And for TID, I'm sure that bipolar parts usually are more sensitive in unbiased conditions. And in case of flash memory, I'm not so convinced. I think we should we should just take a look of some example of flash memory radiation data report and see. Okay, I think that's all.
So I also have several questions, but please forgive me. My expertise is in biomimetics. I was there at ESA, and so I'm not an engineer. But we are designing the mission that scientific mission on the LEO orbit. We know the conditions, the radiation conditions. It is 400 rads per year. The mission will take 1 year, up to 3 years, we will see. And we are trying to use already used passive dosimeters for testing the artificial skin. Yes, so some shelter of the future electronics, and we are trying to use biomaterials, you know, this kind of stuff. So we will have 12 the same type tested already several times in space in LEO sensors that are calibrated already in the company. And the company is telling us that this will be calibrated and you will have a wonderful sensors for your mission. But my question is, because we are going to use different biomaterials, we are going to compare different schemes, yes, of electronics. Should we test all cases, all our, you know, like a sandwich, electronics plus biomaterial, electronics plus, should we all test it separately to be approved for the mission, or we can only test the naked electronics and add our experiment? So.
Okay, so
because it is expensive, as you say.
Yeah, yeah. So
1 hour is very good.
Yeah. So I will not repeat all the question because I cannot. But just.
The question is if we need to test experimental electronics or not.
Mm-hmm. Yeah, but you said it will be 400 rad, yeah? So
yeah, this is.
Is it the ISS or?
It is LEO. It is how many kilometers?
Okay, so
550, 500, 500.
Okay. And you are interested in TID or also synchronous effects?
We are interested in protection of electronics, so everything. So we are building a sandwich really as some material that will be responsible for this, what you beautifully explained. So heavy ions, protons. We don't know also how to locate on the satellite our sensor matrix, because our physicists, nuclear physicists, they are asking, can we assume that the radiation that hits the dosimeters will be always the same, will be exactly the same for all panel of our dosimeters? Can we consider this in our modeling? So this is another question.
Yeah, okay. The thing is complex. I think we can go offline to this.
Yes.
Maybe not today, but
Yeah.
yeah, but we're happy to help if I can.
Super. If there are no more questions, no more inspirations, motivations.
And on chat, it's okay?
Silent.
Silent, okay. They're also tired. So okay.
Maybe I have the last one.
Okay.
Isn't the South Atlantic region and not, it doesn't cover the Bermuda Triangle? It's not the same region, maybe? Because I was saying maybe all of the weird things that are happening there is due to radiation.
Okay, I would expect there are two different things.
Thank you so much.
Okay,
for
thank you
this
again.
very interesting and very much needed for all space people topic. Radiation.
Okay, thank you to you and all the audience on Teams.